Thank you. So I'm going to be talking about GLX and sort of the history of what it is, where it came from, and how it's how we've kind of bolted it into the X server and modified it over the years, and what's various features that have happened. Sort of an archaeological tour, and I'm going to end with things that we've been doing very recently, and kind of where we want to see future work for extending the GLX support, and why that's important for the X server and its success in general. I'm kind of going to go in chronological order, so if it seems like I'm missing something, or if it seems like I'm glossing over something, please just shout, let me know. So what exactly is this thing? OpenGL is just a rendering API. All it really does is it has the notion of various buffers, your front buffer, your back buffer, depth, accumulation, stencil, but it doesn't actually define how you get them, and it doesn't define how you get bits between them. That's all up in the Windows system. The Windows system layer is GLX on the X Windows system. It's Wiggle on Windows. It's AGL or CGL on Apple. There's a thing called EGL for embedded platforms that sort of, you can pretend you don't have to know what the Windows system is under you, and you really do. So GLX is the glue between, okay, you've got OpenGL rendering, you would like it to show up on an X server and an X window, or to an off-screen surface, an X pixmap. So GLX defines how you do that. It's got the X as a concept of visuals, which Windows calls pixel formats, which basically says 8 bits per channel of red, green, and blue, whether or not there's alpha present. GLX extends this concept to include, is there a back buffer or not? Is there an accumulation buffer? Are there depth buffers? If they are, how many bits in each do you get? So GLX adds that. GLX also defines the interaction between GL rendering and all the other X rendering. So those command streams are asynchronous. And so if you want to draw some stuff with GL and then overlay some X text on top of it using the X font renderer, you can do that. Probably shouldn't. If you do, there's explicit synchronization calls for waiting for X rendering to complete or waiting for GL rendering to complete. That's in GLX. Everything else really to do with presentation lives in GLX. So I want to swap buffers, and I want them to present with a particular timestamp. I want them to come out at this moment. That's in GL because it's a Windows system GLX. That's because it's a Windows system operation. The Windows system knows about that presentation. There's things like if you have multiple applications that all want to swap at the same time, you can add swap groups, which are another GLX extension. So multiple applications can all post a swap, and it won't actually happen until the last one in the group has swapped, and then they all swap at once. So anything that involves the Windows system and its interaction with the GL is in GLX. Unusually, it's an X extension, which means that inside the X protocol, there's a sort of a substream that is the GLX commands. Unusually for an X extension, it defines 2 ways that the rendering commands can actually be executed. And these are called direct. It depends on the graphics context. That's called that. You either get a direct or an indirect context. Indirect contexts are the same as everything else in X, where the commands get fed over to the X server, it interprets them, sends them down to the hardware. That's not especially performant. If you have a lot of texture memory, then you have to copy all of that over the Unix socket and hand it to the X server, and then that has to feed it down to the pipe, so to the hardware. So as an optimization, there's direct context where there's this negotiation between the X client and the X server about, okay, the client's going to send commands directly to the hardware, and we're going to negotiate and sort of arbitrate and make sure they don't stomp on each other. So GLX defines the concepts of direct and indirect contexts and how they interact. Different contexts can share some objects if they can share textures or vertex lists if they're in the same address space. So if you have multiple indirect contexts in the X server, they can all share the same textures, multiple direct contexts can't do that, and 2 different direct clients only get their own set of objects. So there's that, that level of semantics. It's all defined inside of GLX. It's worth remembering that GL predates X. GL came about, it does. It does. Keith is looking at me as though it's a lie, but it really does.
Year?
Sorry?
What year did GL start?
I would have to go back and look at that, but whenever the Irish GL came out, which was...
It's like 87, 88.
Yeah, so GLX is like...
You said GL precedes X.
It does, because GL was written, GL does predate X because GL was written for
Well, sure, but X
another
was
Windows system.
developed in parallel at a different
Sorry.
organization.
GL predates GLX is probably a better way to say that. It was written for another Windows system called Iris and then ported to X. Fair. Well, that can't be true because Xterm predates X. So you get the sensation reading the GLX code that the people who wrote it knew a lot about the GL and not a whole lot about X. And so there's some weird quirks that make it unlike some of the other X extensions. The way it does, the way it names contexts on the wire is a little funny. But it's all fairly well written. There's a spec for it, and you can implement it correctly. You just often fail to.
Choose not.
The story for us really starts in about 1999. The 3DFX cards were just starting to be a real thing, and people wanted to run Quake. And in a very real sense, Quake drove a lot of the development of GL through this, at least on Linux. So we already had Mesa, which is a functional replacement for a functional equivalent to OpenGL. But the way it had worked before this point was the libgl API, the client library, sort of faked all the actual GL state. The X server didn't actually expose this extension. It just looked like there was this one that it looked like you were doing a lot of image uploads that were very, very large, and so all your rendering happened in software on the client side in sort of the old build of Mesa. And you can still do this if you want. And LLVM pipe actually does this still. So in 1999, as this was becoming a thing that people really wanted to use Linux for graphics work, SGI open sourced some of their code that implemented OpenGL. They did open a version of the sample implementation of OpenGL, but it never really caught on because we already had Mesa, and Mesa was already good enough. But the GLX stuff, the parts in the X server that implements the wire protocol and managing these objects, we didn't have any code for that. So this was sort of where that starts. The code is still out there. You can actually find copies of it still on SGI's website. And probably one of the best comments in it is this, which is really the story. You cannot implement swap buffers portably. Everything that code did, the entry point for swap buffers, it did all the validation of the arguments and made sure, yes, this is a context that should be able to swap stuff, and this is it's doing so on a visual that's compatible with blah, blah, blah. Then we're just going to call this function pointer, and you'd better write what's behind that function pointer. So that really is a complicated part, and so that's why we've had multiple direct rendering protocol revisions. Is over time we've had to change how we do buffer swaps and how we do getting the bits onto the screen. So when we got GLX at this point in time, the way that the renderer built, so that you have to have a renderer on both sides, right? You have to have a thing that actually draws the commands. It was basically an if-defs magic build of Mesa that took its software renderer, loaded it inside the X server, and it was called GL Core. So all your indirect contexts, which is the thing that you normally get if you don't have hardware acceleration, all your indirect contexts were going through this software GL Core path. About the same time, people started wanting to do actual hardware acceleration and make direct contexts really work. And so the DRI project started around this time as well, led by a company called Precision Insight, who were then bought out by VA Linux at some point. And they got funding from SGI and Red Hat and a couple of other people to work on doing hardware enablement and doing 3D drivers for this hardware. So this is when we got the 3DFX DRI driver, we got the i810 driver, the Matrox G200, and so on. And by 2000, in x86 4.0, the GLX code had been merged. You actually got GLX support as part of your server build. In x86 3.3, that wasn't there. It's kind of surprising to me. I remember 3.3, and I didn't realize that that wasn't there. And 4.0 also changed the driver model that x386 was using. It used to be you had sort of one X server binary per driver. For every single graphics chip that you might want to run on, you had a different X server binary. Well, this makes multi-head really hard if you have multiple GPUs in the same system, because at that time, we didn't really have the concept of multiple outputs on one pipe, at least not on PC class hardware. So it was impossible to do multi-head if all of your if one X server can only drive one chip and can only drive one vendor's chip. If you only had, an ATI card and a Matrox card next to each other, you could run X servers on both, but you couldn't run them as one. So x86 4 changed the driver model so that there was a core that was common among all the drivers, and then individual drivers were loaded like any other kind of plugin, like DLOpen, but not actually DLOpen, and I'll get to that in a second. So, direct contexts. In order to make direct context work, you have to negotiate the resources on the graphics card and make sure that the client and the server don't stomp on each other. The way DRI1, x386 DRI is the extension name in the protocol, the way it did that was approximately the simplest thing that could possibly work. There was a thing called the S area, it's a shared area, which is just a little memory mapped chunk that the DRM driver provided that starts with a lock, a mutex, and a clip list, and a bunch of other stuff afterwards. The clip list is, if you have multiple windows on the screen, where they overlap. You have to know, okay, well, this rectangle I can't draw to because there's another window already there. Well, the X server is the only thing that knows that information, so when the window tree changes, when you drag a window around the screen, the X server would grab the lock on the S area, update the clip list for any 3D windows that were affected by moving that around, and then drop the lock. The reverse happened on the client side. You grab the lock before you go to do swap buffers, you read out the clip list to make sure that you are painting things where you expect to be painting them, and then release them. Note that this means that a misbehaving client can deadlock the server. If you halt somewhere in the driver with that lock held, the X server will never run again because it will try to take that lock and just block forever.
Or by misbehaving, we mean stop the GDB.
Where by misbehaving, Eric points out, we mean you stopped a GL program in GDB, and now you can't type into the X server that's running the GDB session because, yeah, that was pretty priceless.
It sucked.
It did suck. You also have to do memory management. You have to know where the front buffer is. The front buffer is the thing that's being scanned out. The back buffer is the area that you're drawing into that's going to contain your next frame. The depth buffer, which contains, okay, well, these triangles are at these depths in the scene, so I don't have to compute them in the right order. I can just paint them as though they're in the scene, and the hardware will either draw them or not if the depth works out. The X server sets that up in the user mode setting model, and x386 at this point this is all way predates kernel mode setting. So the X server, basically the way that all the drivers ended up implementing it, you kind of pre-allocated chunks for, well, my front buffer is this big, depth buffer's right next to it, back buffer's right next to it, depth buffer's right next to it. You have some more memory for textures, chop, and then all your pix maps for 2D acceleration are in the rest of memory. Totally set up statically at server initialization time, which means that resizing the display, if you plug in a new display and want to get a bigger resolution, there was no mechanism for resizing there. You kind of had to pick things as big as they would ever be up front, and that's why we had the virtual lines in xorg.conf. You had to tell it, this is how big I'm ever going to get. It also meant that since you had this sort of artificial split between the memory usable for textures and the memory usable for pix maps, that you were choosing which of these you wanted to perform reasonably. Inevitably, any choice you make is going to make someone unhappy. It also meant that, I had another piece here. I'll let it pass. But it did work, and it got things on the screen, and you could play Quake, and at 1999, that was the thing to be doing. Note that nothing really happens in DRI for a bit. Like from 2000 to 2003, we got some new drivers, we got some new feature work on GL itself, but there was really not a lot in GLX. EGL 1.0, which is the embedded version of the spec, was sort of there for working on embedded devices where there might not be an entire Windows system like X present. You talk to EGL, this sort of abstracted model instead. That started in 2003. We never really got an implementation of it in Mesa until much, much later, but at least at the time you could see, okay, well, we want this abstraction of separating knowledge of the Windows system from the GL. Then things started getting fun. This is about when I started hacking on stuff. XGL came out in 2004, and XGL was a nested X server that ran as a client of a real backing X server. That was your Xorg or X86. It ran usually full screen. It was itself a direct rendered client, and then turned around and internally did all of its rendering using OpenGL or falling down to software. What this lets you do, among other things, is it lets you write GL-based compositors efficiently, because now you can, since all your rendering is happening in GL, you could do that inside the X server. And this is when Compiz was born. In 2005, we redid how we built X. It used to be this gigantic pile of junk where, in order to build the X server, you also had to build all the client libraries and all of the demo applications, and usually made it very difficult for even dedicated, devoted people to work on, because you could build just the server, but you had to go hack the make files to do it. I make config files, I guess. So we blew it up in 2005. We kind of chopped everything out into multiple pieces. And at the same time, we changed the module format that the server would load. The server used to load just about anything you wanted. It didn't use, everyone know here what libdl is? Anybody not know? It's how you load plugins. It's the runtime interface to the dynamic linker. You point at a shared library and tell the operating system, load this into memory for me, and now I want to be able to grab symbols out of it and call them and use them that way. So this is how you implement plugins. This is how you implement drivers. X wasn't using that. X was using something else that was functionally equivalent in some ways.
Cross-platform portable.
It was cross-platform portable, which was really
For
interesting.
modules.
The idea being that you would want to be able to build a driver on one operating system and run it on another, because there was a period of time where it looked like things other than Linux were interesting. Never ended up really getting used. So it knew how to parse ELF modules and ELF object files, load them itself into memory, do the relocation processing. So all of that was running in your setuidx server, and we had this open-coded everything. Had to port it to every new platform by ourselves. Also had support for loading A.out and coff modules, because those are binary formats you want to support on Linux. We decided that was terrible, and we chucked it, and we replaced it with DL Loader, which just uses libdl like everything else. So it actually made it possible to use normal shared libraries as plugins within the server, and also all of our drivers are now shared libraries. By 2006, the compositing world we noticed that Compiz had existed for a while, and there was finally formally a spec for the texture from pixmap extension, which is a GLX extension. GLX itself contains a notion of extensions, of being able to add additional features to GLX, and texture from pixmap does what it says on the box. Name a pixmap in the X window system and get its contents into a texture so that your client can draw it. And this works with composite because the way composite changes drawing in the X server is composite, instead a redirected window, instead of drawing directly to the screen, draws to an off-screen surface that you can then, that is a pixmap, and you can name it. Between these two things, okay, well I can redirect drawing off-screen into a pixmap, and then I can get the bits from that pixmap into a texture. Cool, now I can write a GL compositor. This was really easy to do for XGL because all the bits were in the same space. It just represented pixmaps as textures internally up front. Xorg did not have this. So we did a thing called AI-GLX, and I wish people would stop saying it. I invented that acronym, and I really wish people would stop mentioning it.
Thank you for inventing an acronym for us.
Do what I can, man. AI there simply meaning accelerated indirect. We had direct contexts that were accelerated, but your indirect contexts were still this software GL core build that I mentioned earlier. We taught the X server how to load DRI drivers the way libgl does.
That's your fault.
It sure is.
That's a horrible idea.
The reason why we did it is exactly the same reason as to make XGL work, because now you have the 3D driver and the pixmaps that you're talking about in the same address space, and you don't need to, so now the texture from pixmap part of this is not, copying data from the client from the server out to the client and then back in. It's just pointer. Oh, it's this part of video memory. There's my pixmap. Go texture out of it. Because again, at this point in life, there was not kernel mode setting. We didn't have that level of memory management in the kernel, so we didn't have any convenient handle to pass between the X server and X clients to say this pixmap is this kernel object, and we're gonna just refer to it opaquely. None of that existed, so AI-GLX was there to kind of bolt this all together and get GL-based compositing in your X server in one process. Horrifying thing, and I apologize, but it does work.
Well, it's got copies running on Fedora.
Pardon?
It's got copies running on Fedora.
Yeah, they got comp is running on Fedora, which was a thing. Everybody wanted wobbly windows, man. So that made it work, but it had, you could kind of see the ugly underbelly happening there, which is that DRI1, again, because it had sort of this fixed layout of the world, there was no way to tell a direct rendering client, hey, your window's been redirected. Instead of drawing to the screen, draw somewhere else off screen. So when you ran compiz and then ran a GL application inside of it, you would see your gears spinning, you'd grab the window, and you could see the window wobbling with the gears punching straight through where they were before, continuing to animate quite happily while the rest of it just kind of, you see the frame wobbling all over the screen. And then once you release the window, the X server is finally told, okay, update the window position, and then the gears would snap to their new location, and you'd see an old copy of the gears up here until you painted something else over it or compiz refreshed again. So direct GL applications would work, but they kind of, you could poke through, and they weren't really integrated with the whole thing. So this is a bit of a problem. Lots of applications would like to use GL. Firefox has WebGL now. You would like to be able to run GL applications and use GL to get the bits on the screen. In order to do this, we really had to have some notion of kernel-based memory management. And so KMS came along. Now we have kernel mode setting, kernel output setup, and that has to all live in the kernel because the kernel is the only thing that knows where the frame buffer is. That memory has to go somewhere, has to be allocated by the kernel instead of being allocated by the X server. So it's got to go. So that all has to get lowered down. Keith is squinting at me, and yes, I know this is, you could do it some other way. Oh yeah, it would be ugly, and I hacked it up at one point with a driver that would tell the kernel, by the way, your frame buffer's here. I don't recommend it. And DRI2 came along at about the same time. This was actually only 5 years ago, seriously, 6, I guess. I went back and looked, and the first KMS driver was i915, and that got merged into the kernel in November of 2008, which is surprisingly recent in my mind. DRI2 then it was a new extension that sat next to GL and kind of replaced DRI1 that did the obvious thing of, instead of pre-allocating memory in this upfront way, we assume that you've got enough of kernel allocation smarts that you can pass handles to these objects around back and forth between the client and the server, and you talk in terms of those. You don't talk in terms of fixed locations on the screen. The S area went away, so now no longer could a misbehaving GL app block out your server. Life got much nicer. That last bit, SWS DRI.so, up until this point, we did the modular X build, but you were still building the software GL core. And the way you had to do that was, at configure time, you pointed the server build to a copy of the Mesa source. And it did a symlink farm to get all the bits into the X server tree, and then dropped out a build of the software renderer that way. This is super fragile. It meant that you were sort of this lockstep. You had sort of this lockstep interaction between which version of Mesa and which server would be mutually buildable. Every time you wanted to refactor how the source was laid out in Mesa, you broke the X server build. So in 2008, we also got what I call SWS DRI.so, for lack of a clever name, because that's what the driver's called. And what that does is it looks a lot like a DRI driver. You load it using approximately the same interface as you load hardware DRI drivers, but instead of being built at the X server build time in this weird, horrible symlinky fashion, it drops out of the Mesa build. So now you can build whatever Mesa you want against whatever X server you want from sort of this point forward, and not have to worry about this horrible interlocking. I feel like I'm skipping things. 2011, we got Glamor. Glamor is a acceleration layer for 2D X drivers that translates X rendering to GL. And Eric did a talk earlier in the week about it. That's very, very cool, and shame on you all for missing it. As I recall, a lot of the reason why that first existed was that on somebody's GPU, you had a binary GL driver and a binary 2D driver, and it was faster to re-implement the 2D driver to translate to their GLES than to actually use their 2D driver, and this was absolutely not a PowerVR chip.
No, it wasn't made by PowerVR.
It wasn't, right. It was not made by PowerVR. Simply looked a lot like one. But this is actually a really cool idea, and XGL had kind of hinted at this earlier, because it means we have to do GL driver initialization anyway. For new chips, we have to make OpenGL work. We're already writing DRI drivers. The acceleration process of handing command buffers down to the card looks a whole lot like the same for the 2D and 3D paths. Let's just do it once in the GL driver and not have to write 2D acceleration anymore. It's sort of the theory here. And we're pretty close. We can actually make that work. And this guy running here is, in fact, all the pixels on the screen right now have been drawn with Glamor. Neat. The inconvenient part there is that we're still loading DRI drivers. We're not loading OpenGL driver. We're not talking to an OpenGL implementation. We're talking to a DRI driver, which has this big dispatch table at the front of it that where all of your function pointers slot in for, here's where GL vertex goes, here's where setting texture images go. So now these two things are fighting. You have any indirect GL contexts that are coming in have their own GL context and dispatch into that. And then you have another GL context for 2D rendering. And it's not merely enough to use the GL call to set contexts. you also have to explicitly know about how the DRI dispatch table works and manually fix it up. So Glamor has this hack, or had this hack, to reset the DRI dispatch table on its way out every single time so that your indirect GL would still work. Ugly. In a real sense, the detail of what DRI drivers are between libgl and the DRI driver, that should be a maze of detail. That shouldn't be something that the X server knows about. So I fixed that. In 2013, I ported the indirect renderer to GL directly. So now it just calls libgl like any other client application. And this blew away, I don't remember what percentage, but
60,000 lines of code?
something between 40 and 60,000 lines of code, because OpenGL is a really big API surface, and every single entry point that you might be able to hit over the wire, you have to generate these little function stubs for. Well, we still generate function stubs for them, but they're much, much smaller. I don't remember what percentage that is of the GLX code, but it was not insignificant.
Most of it.
Yeah. We also got a couple of new DRI, a new DRI, third one this time, and maybe this one will stick. The big difference between DRI 3 and DRI 2 is that in DRI, as far as I'm concerned, is that in DRI 2, swap buffers was a round trip. It was a request that required a reply. So you would post a swap buffers, and you would block until the reply came back. I think I'm getting that right. You can do that asynchronously now. You can kind of throw a swap at the server, and later you'll get an event back, but you're not blocked on waiting for the reply to come back. Other than that, DRI 3 looks very similar to DRI 2 in sort of a conceptual level. There's some details about how objects are named and their life cycles that are a bit different, but that's the big win, and because this makes GLX gears much, much faster, which everybody uses to measure performance. It is
It's not a benchmark.
it is absolutely not a benchmark, and it will not ever be. But this is why Nouveau always looked so much slower than NVIDIA, was DRI 2 was having to round trip. So where are we going in the future? We have now, as I've said, we have the ability to run an X server that uses GL for every piece of rendering, which is really, really nice because it means I might never need to write a 2D driver again. And Eric has bolted this up into a generic driver called mode setting that for the 2D driver that does not care whether you have an NVIDIA or ATI or Intel chip under you. It just says, oh, you've got the kernel mode setting API coming out of the iOctal on this device node. Cool, good enough. I know how to drive those because they're really very similar. So whatever KMS device is under you will come up on it. There will be an OpenGL underneath you that is probably going to be EGL. We still have a little bit of awareness that it is a DRI driver that we're loading. That's how we get the driver into the X server address space. We can make that go away. We can have it just call down to EGL underneath us and say, we're getting an EGL surface, and that's good enough. At this point, we've basically detached the X server from the hardware, which means that we no longer need to use the X server as the hardware display server. You can run something else like Mir or Wayland or whatever you like. As long as there's an EGL underneath it, we can bring an X server up. Awesome. This means that now we can stop adding features to X because we just need to add them to EGL and kind of glue them together through into GLX. But we no longer need to, like, when you add new swap buffers, you just have to write that to EGL. So that should make the X server maintenance problem much less of a problem, which I'm super enthused about because I've been maintaining it for about 8 years and I'm tired of it.
Someday you'll actually stop being a newbie.
I know. Someday I will stop being a newbie. Keith is allowed to say that because Keith predates X. And there are some really cool features that can come out of new OpenGL things that can make the whole drawing all of X through GL. We can make that fast. We're within a factor of 20 for some of the really slow paths, and we just haven't tried very hard and that's for things like core text, not this pretty stuff. But the Xterm anti-aliased kinds of text, we're pretty slow at that. We're way slower than software. But we can get much, much faster if we want to. So it would be nice, and for things like copy area and solid fills, things where there's not a lot of GL banging that you have to do to get the rendering command, we're already within 10% at least of performance of the current acceleration code into the 2D drivers. So with only a little bit more work, we can get the performance to the same level with a utterly generic driver that just knows about GL, and we no longer have to write 2DX acceleration. Really sweet. That's pretty much where I've run out of things to talk about. There's some other projects that can go on in terms of making the GLX better, but they should be less and less relevant as time goes on. So if anybody has any questions, I will happily take them. Yeah?
So how do I get my wobbly windows back?
You can still run Compiz, I'm pretty sure. How do I get my wobbly windows back? You can still run Compiz, I'm pretty sure. I think it's just not maintained by anybody at the moment.
I tested, sadly.
Keith tested Compiz, and it works.
Make sure presenting DRI3 worked with it, of course.
I liked the windows that folded into paper airplanes and flew away.
Yeah, that one, the folding up and the windows folding up and flying away was really cool. Actually, if I'm going to do with my, I guess I should promote GNOME hat on. There is a GNOME shell extension for wobbly windows.
It's pretty poor performing.
I mean, it may be poorly performing, but you are asking it to draw way more than it otherwise would. So I'm sorry that you did that. Maybe don't do that.
No, it's probably trying to execute too much JavaScript.
That could be too. Anybody else? Yes.
This work of its server hardware agnostic,
Mhm.
what I understood based on EGL, will be in the next X server 1.16.
Question was, when do we get this level of hardware agnosticism into the X server as something that you can consume? I would pretty much say one standard deviation per release. If it wasn't in 1.16, I would think that'd be one standard deviation unlikely. If it wasn't the next one, it'd be two standard deviations unlikely. So odds are pretty good. Yeah.
Yeah, I think we can get at least the level of quality that we have on Radeon today working in 1.16.
So
Getting the Intel stuff, that level on the generic driver, we need a bunch of Mesa changes. It's going to be hard.
yeah. So getting it to you could replace everything with this if you wanted, but it wouldn't necessarily be feature or performance compatible. 1.16 seems pretty likely, which will be, I guess, 6 months from now. 1.15 just came out in December, so we're on sort of a 6-month tick. Yeah.
Second question, do the device driver support this EGL yet?
Does the device driver support EGL yet? Mesa has EGL support for at this point all the drivers that it has left, which is everything with a DRI2 port, and so everything that's KMS, Intel, Nouveau, Radeon. There's all an EGL support there. The closed source drivers, NVIDIA I think just added EGL support to their desktop binary driver. They've had it in the Tegra driver for a long time. Sorry?
It's 32-bit only.
It is 32-bit only at the moment because of a really, really stupid thing in the Kronos headers about type defs, actually. Just as an aside, if you're ever writing a project in the future and you feel the need to invent your own type defs, I will hurt you. Just use standardint.h, please. So yeah, most embedded devices at this point, including most of the Android drivers, do implement something that's either EGL or very, very similar to it. So all the open drivers do. We've got at least one closed driver that does, and presumably, if this is important enough for AMD to want to support, they'll add it to Catalyst. That said, there are things that are missing from EGL. There are some workstation features like stereo support, accumulation buffers, bits that are in GLX but not in EGL yet. So if you're using a workstation application that relies on those features, you may have to wait until, you may have to still run Catalyst for a while. And that's still going to stay there. The ability to have to run any driver you want will be there. It's just the generic driver is going to get a lot more capable.
Time for one more question.
Anyone else have one, or I'll answer yours last? Go ahead.
Yeah, sorry, non-monolithic. When do you think X11 will be merged into X11?
When do I think X11 will be merged into the server? Again, 1.16 would be lovely, but I'm not super confident in that. 1.17 seems a bit more likely, and we'll call that, that's again Christmas time next year of 2014. So in this year, it'd be nice to have something in there. Whether that's going to land sort of depends on how much typing we can get done in the interval. It does work at the moment. It's just a matter of integration and testing and making sure that we really hammer out all the details.
Cool. Thank you very much, Adam.